Okay, so the goal of our team is to enable this robot to propel the treadmill, the one that is here, considering that the robot has no prior model of itself, nor of the environment. Also, this should be done in a bioplausible way, meaning that the plant that we are using is a tendon-driven plant. It has 3 direct-driven motors that are pulling tendons, and it has 2 joints. This is done in a few-shot learning approach. And also, the procedure we follow should not rely heavily on error correction. We developed an algorithm called G2P that stands for General to Particular. This bio-inspired algorithm works without simulation and learns and improves a motor skill after a short time. So how does the learning happen? I would like to first mention that our learning algorithm is divided in 2 main groups, the low-level control part and the high-level control part. In the low-level control part, the algorithm starts with what we call motor babbling. Like a baby, the robot starts moving its single leg, and it will go randomly to different points in order to acquire information of what it is capable to achieve. So in other words, it is creating an inverse map from angular positions, velocities, and accelerations to the activations of the motors, activations that are given randomly. Then through a 2D configuration space, we generate the first cyclical movements. Now I'm going to show a video of how this happens. You can see how the robot is going to different points in the space and how the 3 tendons are actuating the 2 joints. It's very similar to how our muscles work. So we have extensors, contractors, and that is one of our main inspirations. This was the motor babbling part of the low-level control. Now, I'm going to talk about the high-level control part, where we have 2 sections, the exploration and the exploitation part. So, as I mentioned before, this is the 2D configuration space where that we use to define our cyclical movements. We have 10 different feature vectors, and we are going to vary these feature vectors first randomly to see what is the system achieving, and then the robot will start moving, generating this cyclical movement, and it will start moving the treadmill. So then we will record this reward, and if the reward is more than 64 millimeters, we will start searching, but with a Gaussian distribution fashion. Now the reward will be increased more, and then we will reduce the standard deviation of this search, and we will only search in the vicinity of the already very good solutions. So then we will see that the movement is going to improve, and the reward is going to be increased. I'm showing now a video of how this happens. Should play. Yeah, but I don't have the mouse here. Okay. Perfect, yeah. So you can see how it has no reward at the beginning. Then the reward is negligible. And the inverse map that I described at the beginning is going to be refined each time that we do an attempt until we get really high reward, and we see how the system is learning to propel the treadmill backwards. Next, I would like to mention some important concepts in order to show you the results we got to. First of all, everything what I have described so far is a run. This run consists of motor babbling, generating the inverse map, that is from positions, angular accelerations, and velocities, and then generating numerous walking attempts. One attempt is 20 steps, and after each attempt, then the inverse map is being refined. Also, it is important to mention that each attempt generates a solution, that is the treadmill reward. In other words, every run generates a family of solutions. In the next figure, I am showing I am contrasting different families of solutions. Here we can see in the x-axis the number of attempts, and in the y-axis the treadmill reward. This line is the threshold between the exploration and the exploitation part. So we focus in this family here, the green one, G. We can see how it took approximately 60 attempts to cross the threshold. When the threshold was crossed, the treadmill reward was increased in a much rapid fashion. So this is the Gaussian distribution part. This is the random exploration part. And something very important to mention here is that each family is different. So we can turn off the system, then we can turn it on again, and it will find different solutions. It will behave different. That was something that excited us a lot because we said, okay, so the system is kind of acquiring different personalities each time we turn it on. It's getting to different motor habits. So each family found a different motor habit that is a different way to push the treadmill backwards. Now, I want to show the same families of solutions, but in a slightly different way. Here I am comparing the mean power of each attempt against the treadmill reward. All of these are convex holes, and they have inside all the attempts that were performed. We can see that, for example, for the family I, the mean power was almost always the same. So the treadmill was being pushed more and more and more while the system was improving, but the power was kept approximately the same. That was really interesting for us because we were thinking, okay, maybe if the system is pushing more the treadmill, there will be an increment in power consumption. Or maybe if the system is learning to push a treadmill, then we will see an emergence of optimality, like it will be more efficient doing this task. But we didn't see any of those. We saw how each of the families keep approximately the same power consumption. We can also see how different families have different regions in this space. So that is an opportunity for us for future research, because we are like very impressed of how different solutions emerge. Now, this is what I already explained to you. So this figure, the dark one, we are not seeing any of the families having this elongated shape from left to right. So we conclude that more propulsion is not more energetically costly. Also, we don't see any shape like this, meaning that no energy minimization in a single family of solutions. I also want to show you this video where the system is has already learned a cyclical movement. Then we perturb the system, and we see how it persistently keeps this walking cycle. I don't know why it's not running. Yeah. So this is a video of how it learns something. Then we add some perturbation, and it goes back to what it has already learned. It can also learn more complex trajectories, like point to point. And we did this after we got some reviews. They wanted to see how robust is the system, so it performs different trajectories, not only the cyclical one. Okay. So towards the future, our algorithm that I already described is called G2P, and we want to test this algorithm in different anatomies. So we already tested in a 2-joint 3-tendons system. We want to test it in more joints, more complex systems. We're looking forward to try it in a quadruped, also in a biped that we have already started constructing. And we want to try different tasks. For example, a standing task, where we will need to generate downforce. Also, alternative bubbling strategies, meaning this that maybe we can do some bubbling strategies based on curiosity, for example. And more levels or hierarchy in our control architecture. I want to thank our funding support, and thank you for listening. But before finishing, I want to put this question here of what will be the outcome of using this algorithm, G2P, on language, balance, or maybe recovery after morphology alterations. Thank you very much.
Oh, wait.
Yeah, sorry.
Thanks. I just had a quick clarifying question about dimensionality. So the state space here, I guess, 4-dimensional, or maybe 2, since it's fairly heavily damped, it looks like. Is that about right? And then what's the dimensionality of the control action space? How many, say, decision, is this something in time, and you make a certain number of control actions in time, or how is it parameterized, basically? So
how it is parameterized?
Yeah.
Like, that's your question, right?
Yeah. How does this grapple with the curse of dimensionality, I guess is what I'm
So, okay, so we use a 2D configuration space, which is formed by 2 angles, what we call the hip angle and the knee angle. And we have 10 feature vectors, which are like in a cyclical fashion. And this is 2 dimensions because we have 2 angles, 2 joints in this case. Let me go back to that figure, this one here. So this is the configuration space that we're using, and in this case is 2 dimensions. Now, if we see it from the hardware perspective, we have a 3-dimension space because it has 3 tendons. So the inverse map that we are using goes from 6 inputs that are these positions and the accelerations, and the velocities and the accelerations, to 3 outputs, which are the activations of the motors that initially are random.
Okay. And how do you discretize the space?
We run the system in 80 hertz, and so this is the frequency with which we are acquiring the data, and then acquiring the data. And then we do this, and the next step is to refine the inverse map, and then we try again.
So let me ask it a different way. How many separate numbers are required to characterize the controller?
6.
For gate cycle.
For the full gate cycle. Not at a given point in state space.
Okay, 6.
Because 6 numbers to describe the entire controller.
Yeah, those are the inputs of the artificial neural network.
He's wondering how long is the trajectory? How many points do you have control?
Oh, okay. So it's 10 points. We're using 10 feature vectors, as we can see here. If we count all those points in this cycle, these are 10 points. And then we are varying these 10 points, as I have explained, in a totally random way or in a Gaussian distribution approach.
So is it 60?
I guess the number is 60, is that right?
Yes, yeah. If we see it that way, yes.
Yeah. Pedro Moraes from Oregon State. So I was wondering, why do you call this locomotion and not manipulation? Because you don't have a vertical degree of freedom. So for a lot of the state space, you're basically completely actuated and stable.
Mm-hmm.
What is the distinction?
We call it locomotion because it is performing a functional limit cycle, meaning that it is pulling the treadmill backwards. So it is, in that sense, it is constraining our system, of course, but it is pushing the treadmill backwards. So that's why we call it a locomotion cycle.
Would you also call juggling locomotion?
Sorry?
Would you call juggling locomotion? It feels like if you take this and turn it upside down, maybe it's juggling.
Yeah, it will be very interesting to see that because it will need to know the position of that thing that is juggling, or it will be a little bit more complex, but perhaps, yeah. That's the thing, that we want to test this with different tasks. Yeah.
So I feel like one thing that this would benefit from is some sort of gold standard by which to compare it against. So, like, you demonstrated that you can learn to do this in a way. but I imagine that there might be a way to do it much, much faster. And have you thought about what
Much
that
faster.
is? Yeah.
So that's something I didn't mention, and thank you for bringing that up.
Yeah.
This bubbling, together with the learning, happens in approximately 7 minutes. So the bubbling part takes 5 minutes, and then the refinement can take 3, 4, so it's less than 10 minutes actually. We consider this something that is actually fast compared to other learning algorithms that we have seen. And also I want to highlight what I mentioned, but just very quickly, that this is done without simulation. So everything happens in the plant, having this a lot of advantages.
So it seems like the other learning algorithms you're talking about were they applied to your system?
That is something we need to test,
Yeah.
and those are some steps for our future research.
I was going to ask the same question.
Okay, maybe we can thank our speaker.